Right. Thank you all for coming. Yeah, today I wanted to talk to you all about some coverage metrics for compiler-generated debug info. But first, to kind of set the stage, let's just take a look at a simple function. It's not too important what this does exactly, but just a simple function takes some input. There's a loop, prints out some output. If we look at this function, there's this variable sum that we'll focus on throughout this talk. That's defined maybe halfway down the function, and then assigned, and later we read from that variable. So if we were in the debugger trying to stop kind of just after the first place that variable is defined and try to print that out, what might we see? Now, if everything's present and correct and working as we would like it to, we would see sum equals 0. That's the current value of that variable. But we may also see all sorts of other things. We may see variable not available or optimized out if it's an optimized build of the program, or if there is debug info there, but it happens to be wrong for some reason, you might just see some sort of garbage value. So this particular work focuses on measuring the coverage of that information, so checking the cases where the variable is maybe not available or optimized out because it's not present in that compiler-generated debug info. We're not checking the case where it's present but maybe wrong. Although we do, my colleague Stephen Kell and I do have some
registration desk if you need
to be checking those as well. Just a super quick intro to debug info. I imagine maybe quite a few of you in this room are already familiar with debug info, but if you're not, this is the very super fast intro to debug info. So taking a look at just a portion of that same example, kind of the main loop, the function I was showing before, there's some instructions that might be generated by some compiler to map to those source lines, and then some of the aspects of the debug info that we're interested in, particularly for this coverage approach, are the line table. So mapping from the line table in formats like dwarf lets you map from a machine instruction back up to the source line that caused it to be produced, and then for each variable that's like in scope, you'll have a location expression that's telling you where the debugger could find the current value of that source variable. So, for example, here you see that for the first bit of the function, there's just like the literal constant value 0 as the location. So it's not looking it up actually anywhere in program state, but it just knows that value has been, or that variable has been set to 0. And then as the program progresses, it gets updated to say it's in a particular register. And those expressions can get more complex, but this is just a basic intro. And then now, if something happens to go wrong, say an optimization pass might drop debug info, or something else might go wrong. It could be the case that we only have sort of partial debug info for that variable, and we just might not know what it is later on in the program. So that's an example of a situation we would want to be able to check with this kind of coverage work. So if we think about what some good properties of a coverage metric for debug info might be, we want to find a metric that helps us focus compiler efforts to make debug info better. So really the goal of this is we want the debugging experience to be better overall, and by having a good coverage metric, we can use that to kind of drive efforts to improve debugging overall. So what are some properties of a good metric? It should be independent of the compiler used. Like you would want to be able to test it on, you wouldn't want it to depend on specific compiler internals or options that are specified. You want it to be possible to achieve 100%. That might seem like a trivial thing, but we'll get into that in a moment. And also, it would be good for it to kind of be free of anomalies. I'm gonna go into more on what that might mean in more detail later. Yeah, okay, so coming back to the same example. So if we take a look at what an ideal compiler might output for this and measure it by some existing tools. So there's a variety of tools already that do measure coverage. So there's a tool called Debug Info Quality. There's LLVM. Dwarf Dump itself has a statistics view that will take in the dwarf debug info and output some debug info coverage stats. So if we look at what those existing tools will do, they measure coverage by looking at the instruction bytes for the function and measure the described instruction bytes over kind of the scope of the variable. So you'll have to just trust me that these measurements of instruction bytes that I put on here in very tiny font, I guess, at the bottom are actually correct. It was I couldn't really think of a way to also jam all the instructions from the function onto the slide. But if we're looking at this variable sum, we find that the whole scope is in this random compiler I was trying. The scope ended up being 112 instruction bytes, and then the area that's described for that variable sum was like 63 bytes. So if we use that particular metric, we see, okay, 63 over 112 instruction bytes covered. That's only 56% coverage. But the interesting thing is that, I mean, really, this compiler probably did everything it was supposed to do. It has described that variable from the point of where it's first defined to the end of the function. So, really, you'd hope that would be more like 100%. But with this metric that's often used today, you don't really have a way to get to 100%. And it's also not really independent of the compiler. Like if you imagine, since we're measuring in terms of instruction bytes, basically anything that changes in the compiler could change the number of instruction bytes that are used throughout the function. So that would then affect the coverage score that you get with this kind of approach. So a different compiler, different optimization options, any of those sorts of things could affect this in a way that's not really about debug info coverage itself. And then it's also, this is sort of affected by some anomalies. In particular, whether you just allocate all the variables on the stack versus a more optimized view where you actually put things in registers. So if everything was just placed on the stack for the whole function, you would get a great score here. You'd get 100% coverage because the variables are all accessible. But in an optimized program, particularly, that's not what you're going to see. You're going to have things moved into registers, and so this kind of penalizes doing the correct thing when you use a metric like this. Right, okay, so just to kind of summarize all that, so these existing tools measure coverage in bytes, which is hard to compare across compilers and also different options of the same compiler. And it doesn't really line up with the user experience either. If you think about that, like you'd really like to have, there is value to measuring it at the level of instruction bytes sometimes, but I think it's more important to be closer to sort of the user experience, which is often at the level of stepping through source lines, and you'd like to know kind of what your coverage is there at that level of source lines. And also, existing tools sort of use the full scope of a function or a block instead of just the area where a variable might be defined. So it can become impossible to sort of achieve full coverage. All right, so let's take a little look at the approach we were kind of coming up with in a few steps. So we tried to think of what a more accurate approach might be to measure debug info coverage. And so one of the things we changed was, let's try to look at this in terms of source lines. That will kind of better match the user experience, and it also gets around some of those compiler-specific and option-specific issues we were talking about before. And then we want to look at, for each variable, we want to measure just the coverage in that variable's defined region. Okay, so coming back to this example again, so if we try to, again, look at what an ideal compiler might do using this approach in terms of source lines. So we see here that the variable is defined over, well, if you start from like just after the first line where it's defined, it's defined over those 8 source lines, and then this ideal compiler has described it over all 8 source lines. So hooray, 100% coverage. And so that's independent of that compiler. It's possible to achieve 100%. Now, okay, is it free of anomalies? Not necessarily as you get away from an ideal compiler. So we'll talk about that in just a moment. But first, I just wanted to say about this achievability issue. So this chart here is just showing all of the variables in the Git code base as an example. So on the x-axis, this is just all of the variables that exist across the code base sorted by their coverage. And this is trying to show, when you compare the two approaches that's used by, so our approach versus the one that's commonly used today by many tools, This sort of gray corner in the top right there is all of the coverage that other tools claim exists, but is not actually achievable. So for some variable in that gray zone, you might get a result of 80% with existing tools, and that might actually be the best you can do. But it's hard to know because it's not 100%, and you don't really you can't be sure very easily. So that just gives you some idea that there is quite a lot of space out there that is hard to represent with existing metrics, and it would be better to have something that always gives you 100% by tracking kind of from the point of first definition, as I was saying before. Yeah, okay. Let's see. So now, if we take a look at a slightly more realistic compiler, it's often the case that compilers don't actually describe all of the lines that I'm showing in this example. So, for example, let's see, like for the blank line especially, that's unlikely to be described. The closing braces are often not necessarily described. So if you apply kind of the initial approach I was describing before, you'd see here, okay, maybe this compiler only describes 6 of the source lines forward from that variable. That gives us 6 out of the 8 source lines. So it might appear like that's 75% coverage. Okay, not necessarily what we wanted to see. Or, we might get a different compiler that does a slightly different thing with the source lines. Okay, this is 6 slightly different source lines, still not quite what we'd like to see. So what can we do about this? Well, we thought about this for a bit and kind of realized that compilers are only emitting debug info for source lines where there's some amount of computation happening. So if we could just add essentially like a static source analysis pass to find the parts of the source program where there's some amount of computation, we can use that to sort of filter out the source lines to only consider ones where there's some computation happening. So if we do that again in this example, there's six lines essentially where there's some computation happening. The compiler described 5 of them, so that gives us 5 out of 6 source lines for this example. And that really kind of achieves all of the goals I was mentioning earlier of having an approach that is independent of the compiler. It's possible to achieve 100% for all variables and free of these kinds of anomalies of stack versus register usage and those sorts of things. Right, so this is just to restate kind of the revised version that we ended up with in the end is we're looking at coverage in terms of source lines to eliminate issues involving instruction bytes. For each variable, we look at the coverage only in the region of the program where the variable is actually defined forward, and then filter the source lines to those with some kind of computation happening. Okay, so we did a number of experiments using this approach. Just to start off with that, I guess, the status of the tooling we implemented here is we've built a tool to calculate this coverage metric using the compiler emitted dwarf as the input, and then it also adds on this baseline using the source analysis that I described before. There is a research prototype, I guess I'd call it, available with a recent paper that we published on this in the CC conference. But yeah, more on that and kind of future work towards the end of the talk. Okay, so let's take a look at measuring some coverage with this approach. So this is, again, a chart looking across the Git codebase, all the variables in Git, and just checking that using our approach in both Clang and GCC at different levels of optimization. There's a lot going on here in this chart. So you could probably stare at this for a while and ask all sorts of different questions. But I guess, let's see, what are some of the things that stand out? I mean, I guess one thing I'll say is that in many programs, and in this example, once you have some amount of optimization enabled, just O1, or even whatever the basic first level of optimization is, there's quite a few variables that are, at least missing one line of their source coverage. And some variables are just, entirely inaccessible for various reasons. So I guess I just want to highlight that there's a lot of room for improvement in debug info. If you're interested in debugging workflows, there's a lot of work that can be done to really improve that and give everyone a better experience, especially with optimized programs. Let's see, what else to say from this? So yeah, I guess with optimization on, there's kind of 2 frontiers that do the best. I mean, it's not too surprising, like the OG mode from GCC and it's probably the best of the kind of published official modes that exist out there. That's kind of trading places with O0 plus mem to reg in Clang, but then and then O1 in Clang is a little bit behind that in coverage as well. So anyway, lots of things you could glean from staring at this for a while. I also wanted to mention that we tried to do a replication study. So there's a recent paper in ASPLOS 2023 that examined debug info coverage over 5,000 C-Smith generated programs. And so we tried to make our approach kind of look a little bit more like theirs. They did something different rather than using the sort of emitted dwarf info. They were kind of exploring things more dynamically by attaching a debugger and looking at what it shows for each variable. So in trying to make our approach look a bit more like theirs, essentially, I'm going to go pretty fast through this part, but essentially, we saw similar trends that kind of validated what we were doing. Their approach doesn't give you an absolute value. It's something that's relative to O0. So with that in mind, essentially we saw things that made sense when you take those attributes of the approach in mind, and we're able to present some metric for O0 as well, whereas theirs are relative to some optimization level compared to O0. But there is more detail on that in our recent paper. If you're curious about the replication study, there's also many more bits of info about some details like how to handle inline functions, case studies looking at specific compiler issues, and also some kind of more forward-looking ideas of how we could potentially extend coverage, improve coverage without too much more work, and also looking at some recent dwarf extensions like location views that could help with these kinds of things. Okay, and then just to talk briefly about future improvements. So the version that exists of this right now is just a very it's very researchy. It would be a bit tricky to use, I think, for most people. So we'd really like to continue developing this towards something that's for regular use. I'm imagining likely building this as a new coverage mode in LLVM dwarf dump. But I'd like to start an RFC thread on Discourse and kind of just see what the community thinks is the best way to go. I'd also love to explore ways to make this more easily accessible on an ongoing basis. So if people have ideas, please do come up and talk to me. I mean, things I've thought of already are we could be including some of these metrics in compiler explore views. We could be adding them to the existing debug coverage metrics that exist in the LLVM nightly testing. There could even be like a pre-merge metrics comparison view, similar to the LLVM compile time tracker that would let you kind of see the effects of debug info work before it merges. So yeah, I'm sure there's even more ideas out there of what could be done. So if you do have some, do let me know. And yeah, just to summarize this, so the debug info today often gets a little lost or confused, especially
registration desk if you need
program. So this work is taking a look at some improved ways to measure coverage metrics, the completeness of the source coordinates and variable location information in the program, to measure what's currently been lost as a way to hopefully help people spot any loss and improve compilers going forward. And also my colleague Stephen Kell and I both have some ideas for future work as well that could actually check the correctness and not just the presence of values for variables as well in the debug info. Thank you.
Thank you. Do we have any questions?
Joke from Corey. Thanks for the talk. Do you have any tool, for example, you select which lines your variable is actually alive, let's say.
Yep.
Do you have any way in the verifier that actually says if it's covered in 100%, but it's actually really covered in the 100% of the lines I find it's alive? For example, debugging C++, multiple times I get into end of a bracket and it stops over there because it's the structure of a structure. And I'm like, well, that comes from the library and it seems alive over here, but you don't see that in your source code. So maybe sometimes you can not account that line, another one, and it's actually not what you want.
Okay, we might have to talk more about this separately. I'm not sure I'm fully understanding the example, but I mean, there are a variety of issues like this, I think, where there's like some nuance to how you count the lines, and it is something that needs a bit more refinement, I think, because I think there's various special cases, probably like the one you're mentioning, where, yeah, there's some details that would need to be tweaked there, and I think that's another thing that would be great about getting this kind of into the mainline code base upstream of LLVM, where lots of people could be helping with these kinds of things, and I'm sure there's many that I haven't even thought of. So yeah, thank you for the question.
Yeah, thanks for the talk. Maybe it's included in your paper, but I'm really wondering how did you deal with the source code duplication problem, let's say, in the case of inlining or loop peeling or loop unrolling, the source code's been duplicated in multiple places. If, let's say, some of the places got the debugging for, but some other places does not have this variable live information, then how would you measure it? Let's say, okay,
yes. So yeah, there's definitely some information about like specifically the inlining case in the paper. Let's see, I'm trying to page that back into my head at the moment. I think the short version is that so for an inline function where there's lots of different copies of the function, we essentially just average across all those copies. So we'll look at all the copies and then just say whoop, and then just average across them. Yeah, the other one you mentioned about loop transformations, loop peeling. I don't know if we did anything specific about that, but potentially that same kind of inlining approach would also handle that case as well. I don't know. I have to look more closely. But yeah, thank you.
Yeah, my question was also about inlining, outlining, and all sorts of optimizations. I don't know at which level we are going to handle that. I mean, do we have separate analysis for separate optimizations or?
So, I mean, with this particular work of measuring coverage, like for inlining, say, you should have, you'll have some amount of information in the dwarf debug info or whatever debug info you're using that's describing kind of each inlined copy. And so then we'd be able to examine across that, combined with the source analysis of just the program for the stuff that was inlined. And that's kind of as I was saying with the last question, like then we could either average across that, or you could even do something fancier, like if there's, if you wanted to weight them differently, depending on how many times a certain copy is used, there's fancier things you could potentially do there. But yeah, I don't know, does that sort of answer your question or, yeah, okay.
I have a question of my own. The source analysis that you mentioned, how much does it need to know about the programming language? Does it look just if there's an empty line or?
So it's just it's a pretty simple analysis across, but currently we build it on top of the Clang AST, like a Clang tooling type tool. And yeah, it's just kind of thinking about different AST nodes and trying to imagine which would often have computation. But there's definitely some nuance there that would need some refinement where like currently there are some cases where we sort of just assume this particular AST node should always have computation, but that's not necessarily the case in practice necessarily when you get all the way down through code gen. So there's things like that might need some refinement. But I mean, it's a fairly, I guess I would say, simple static analysis pass. The one we have now is only considering C cases, not C++ yet, for example. But it's pretty easy to adapt, I would think, for any language. Yeah.
So does it run during the compilation and produces metadata that is available afterwards?
So at the moment, it's sort of just a separate tool that can kind of integrate with the build process and outputs kind of an extra metadata file, essentially. I'm imagining that's one of the parts that I would change entirely, I think, like that makes it a bit hard to use at the moment. So yeah, I'm thinking right now, if this was kind of pulled into the LLVM dwarf dump approach, I would imagine maybe using something that can leverage like the compilation database to sort of revive a Clang AST, and then from there do the analysis so that it's all kind of enclosed inside one program rather than kind of a crazy pipeline of researchy things like it is at the moment. But yeah.
Thank you.
Yep.
Any more questions?
Hello. Thank you for the talk and working on this tool.
Yep.
This is more of an observation than a question, so
Sure,
it's not particularly helpful. But if you tie the coverage metric to line numbers, then the metric also gets affected by the quality of the line table.
Yes.
So that may be a desirable property for it or not.
Yeah.
I think in general it is.
Yeah.
But yeah, I just wondered if you thought about that, had any particular thoughts on how that comes into play.
I mean, yes, you're definitely right that yes. I mean, we are using the line table to map up from the dwarf debug info for each variable is in terms of instructions, and so we have to use the line table to map that back up to source lines before we can kind of compute coverage. So it definitely does depend on an accurate and correct line table. I think it's a good choice. I think because, like you said, it sort of depends on having a good line table. So that's another factor that we would want to see improved. And it lets us kind of get to that level of source lines where the user is working. So yeah, I mean, I think it makes sense, but I suppose some people might argue it's maybe not the best. But yeah, I don't know.
Yeah. So my question is, you've covered the case where you measure from where the variable's declared.
Yeah.
But in reality, especially when you're optimizing, after its last use, you're probably not going to describe its location. So are you expecting an entry to put in to say it's optimized away up to the end of the scope?
Right. Okay. Yeah. So that's a good point. Especially if you had a very large function, say, and something that's no longer used, way earlier on, the compiler might not describe that. I guess in conceptual terms, we are expecting that it would be described for that whole enclosing block, whether that's some nested block or the function, because it's at least possible to do so. And we actually have, that's actually what it relates to this knowledge extension thing that we go into in the paper, where we have some ideas about how you could fairly trivially just kind of tell the debugger to keep a copy of essentially like the last value of a thing if you wanted to keep a variable alive for the rest of the function. But you're definitely right that it would be common for things to maybe just not be described after the last use. Yep.
Thank you again for the talk, Ryan. Our next talk will begin at 11:30.